we've done our homework and we know basically how we could do these dynamic mechanical testings. We know how to run those experiments. Now let's get into kind of the fun data analysis component of this section, which is really cool, very visually intuitive, and a really nice way that you could kind of start to analyze and deduce polymeric material. So this is our loss modulus again. So let's just define that. It's going to be our loss modulus. So again, this is our viscous, our out of phase, viscous, out of phase versus our storage modulus, which is our, again, that in phase component, that elastic response that we were working with here. So it's going to be in phase, elastic, solid material, viscous fluid. So what you'll find most of the time experimentally is that you're going to see that at a fixed temperature, our loss tangent is going to be basically very small at very low and very high frequencies. They're going to peak at intermediate frequencies. Peak at these kind of intermediate frequencies, kind of similar to like our basically nucleation and growth. Why did we peak at intermediate undercoolings? Well, our storage modulus, again, E prime, that is going to be high at high frequency short times. Again, that should make sense because polymers will behave essentially glassy or elastic at high frequencies. Remember, when I pulled my silly putty quickly, it basically fractured, behaved like an elastic solid at again high frequencies or short times. At low frequencies, i.e. longer times, the polymer will behave more like a viscoelastic fluid. Thus, E prime, that contribution, E double prime, that contribution will be essentially larger. So low frequencies, longer time, that contribution is going to be larger. So at these extremes, one of these will be high, one of these, basically one of these will be very large, one of these will be very small, and again, we're not going to kind of peak in terms of our at very high frequencies, very low frequencies. So this value will be maximized at those intermediate frequencies. But more importantly, you'll often see graphs. Sometimes you'll see graphs of tan delta, and again, we could kind of intuit what those polymers will look like and behave like. But more often, from that graph and that analysis, more often you'll see here this type of graph. We're plotting G prime and G double prime is basically similar notation for essentially E prime. Effectively, we're saying the same thing except we're looking at the shear moduli. This graph is incredibly important because it allows us to kind of visually see and determine what frequencies or at what frequencies in terms of when we're basically mechanically testing our material, the polymer behave like an elastic solid or an elastic or a viscous fluid. So let's look at, again, short times, or excuse me. So we're looking at small frequencies, low frequencies. Let's say that this is hertz. Low frequencies, which is higher? Our G double prime, our out of phase component, our viscous component. And that should make sense because at long times, it should behave, long times, low frequencies, we should behave like a viscous material. This behavior dominates. The higher curve, the higher, this kind of moduli, that's the behavior that dominates. So at this time here, we're behaving like viscous. But at high frequency, short times, we are behaving, again, this moduli is higher than this moduli, we're behaving like a solid. And this crossover point is a critical point. That's where we find our characteristic relaxation time for our polymer, that intersection where G prime, G double prime essentially intersect. So this is an amazing, just think about this. Depending on your polymer, you could run this quick experiment and see, okay, I can figure out the characteristic relaxation time, and for my material or for my application, is my polymer behaving like elastic solid or viscous fluid? Amazing, right? This result is really, this is such a powerful technique. And you can even take it a step further. And actually, you'll typically find these values, G prime, G double prime, and specifically tan of delta, are going to be plotted as a function of temperature here. So we're going to look at that in the next video. But this is kind of the key takeaway from this dynamic mechanical testing. So be ready to kind of be given multiple of these curves, multiple relaxation times, and correlate that to kind of polymer structure and mechanics. So I'll see you all in the next video. Thanks. Bye.